Right. So I'm hoping you can all see that. Jenny, can you just give me some indication that's what you can see with my first slide?
Yes, you're all right.
Very good. So thank you for that introduction. Now, I actually am from Australia, so I know where Castlemaine is. And and I've started, I think, in my career back at CSIRO in 1987, sometime last century, working at CSIRO in Hyatt in Melbourne. And that was my introduction to cheese science. And so I've been working on cheese ever since then. So it's about exactly 34 years now. So don't ask me any questions about seaweed because it's not really my expertise. I just happened to get some grant money to work on a seaweed project, but I think I can picture what seaweed is, but I can't really explain what it is. So let's stick with dairy products here. So as Jenny pointed out, I work at an institution called Ag Research here in New Zealand, and I've been here for most of the last couple of decades. And I also work at another institution called the Everett Institute, and this is a partnership between Ag Research and Everett at the Massey University campus in Palmerston North. And there's our lovely building there. It's a 3-level building with state-of-the-art labs, and it's just finished last year. We were just about to move in, and we had our one lockdown, which was back in, oh gosh, when was it? I guess it was March, April last year. That was our first and only lockdown. So that was a bit of a shock to the system, but we did manage to move in all right. And it's quite a productive partnership between those two institutions. So I'm a cheese structural scientist, physical chemist by training. So I'm going to talk a little bit about what cheese structure is and how it can be manipulated to create flavor in cheese products. So let's go ahead and let's see if I can actually change the slide. So these are the most common, a little bit of background information here. It's kind of fun to start out with just some introductory dairy chemistry and production. So these are the most common dairying mammals that are found in the world. And as you might expect, the bovine cow is the most common one with about 84% of milk production worldwide. The next one is quite surprising. It's a water buffalo. In this case, looks like the water buffalo might have a glass eye on its left side there. That's a rather interesting picture. And a lot of that is due to the fact that India produces a large amount of milk, of which 60% is buffalo. And of course, as I'm sure you all know, mozzarella cheese strictly should be made with buffalo milk around the Naples region in Italy. So the next one is the goat milk, followed by sheep milk, and then followed by camel milk. And I only know of one company, you may know of a few more camel milk companies, one in Saudi Arabia. It's called Camelicious, and they make camel milk yogurt. And it's not that easy to make decent camel milk cheese, but there is a lot of research going on to take the chymosin from camels and use that in bovine milk cheese manufacture for various reasons. So starting out 8,000 years ago, which is always a good place to start, first of all, how was cheese developed? It was probably discovered by accident, and the first thing that's required is some kind of mammal. In this case, it's probably a sheep, I think. And the next thing you need is to be able to milk it. Then you need some way to clot it. And back 8,000 years ago, there were not a lot of plastic jugs around, so milk would have been stored in something like a stomach. And if it was stored in the fourth stomach of a ruminant, then it would have had that clotting agent built into it, chymosin, which would have clotted the milk over time. That's not the only agents you need. The next one is some kind of agitation to break up the curd structure to introduce what's known as syneresis, followed by some heating, and not that much heat that you can see there in the sun, but something like usually between about 38 degrees and 55 degrees, depending upon the type of cheese you're making. And then at the end of the day, the nomad would have undone the stomach and expected to find milk, but would have found curds and whey. So a separation is required at that point to make cheese. So a very rudimentary way to make cheese back then. This is probably how it was serendipitously discovered. So milk and cheese consumption is shown here, and I try to update this most years when I can get the information. So the latest I got here is 2017, and you'll look at all the countries down there, down to the 13th ranked. And if you look at all of those, where are all those countries? What do they all have in common? I think I've given you a hint there. Where are they located? and they're all European countries. And that's where a lot of the development has taken place over millennia on cheese, different kinds of cheese varieties. And then you see Australia down there, 26th, and New Zealand, 32nd. And looking at the amount of cheese we consume, it's something like, well, over here, it's just a little less than 10 kgs per year per person. And in Australia, it looks like it's something about 13 kilograms. That's going up, by the way. Up the top there, you'll see that there is roughly 655 million tons of milk produced per year. And cheese production is something like about 21 million tons. Right, let's see if we can push this forward. So where is cheese consumed? And of course, it's the obvious answer is where it's produced. And if you look at these countries here, the darker the color, the more cheese that's consumed. And a lot of those countries, the bulk of them appear to either be in Europe, including Russia, and Australia, New Zealand, South America, North America, where European immigrants traveled to. And so that's the history of cheese. And because of that, we consume cheeses because consumers appreciate it more in those countries, although there is a growing cheese market in places such as China and Japan. So what causes differences in cheese varieties? So it's a number of things there, but first I'd like to point out that cheese only contains 4 things generally, unless it's something else like processed cheese, and that's milk, culture, rennet, and salt, by and large. So things that change the variety of cheese, and you'll see at that upper picture, there's a number of cheese types that I took in a market in Cork in Ireland. And down the bottom there's another market. And if you look at the printing on that sign, just send me in the chat box what country you think that's from, and I'll take a look at the answers as I'm talking. So this is some cheese I took, and I think the audience, at least the shoppers around me, thought I was rather peculiar taking pictures of cheese, but we don't get a lot of cheese displays looking like that here in New Zealand. So things like milk composition, the kind of way that's made, called the make schedule, the starter culture, secondary flora, things like smear ripening, the ripening conditions, very important. The obvious one is also the type of milk. Partial separation of milk. If you're making Edam cheese, for example, it's about a 1/4 reduction in fat content. So you start with slightly skimmed milk. Pasture quality. There's a lot of research done in Ireland and Switzerland to look at what do the cows eat and what impact does that have on the flavor profile of the cheese. The seasonality has a little bit of an effect. And if you're a big cheese manufacturer, that's something you want to eliminate because you're in the business of making cheese that's obviously safe, but also that is consistent in quality during the year, so the consumers don't get any surprises. Very much unlike the wine industry, I should say. The type of coagulant, as I mentioned, chymosin from camels. There's fermentation-produced chymosin now, and of course, it's chymosin itself from calves, and different kinds of microbial cultures, particularly one from mucor mihi. It's a protease found in that particular cheese, which would, I guess, make vegetarian cheese. You can make cheese from a number of things, not just milk, but cream, skim milk, and whey, although it's open to debate whether whey cheese is actually a cheese, if you've ever tasted it. It reminds me of the smell of moldy carpet, I have to say, some of those whey cheeses. And also the pasteurization, heat treatment effect. That does have an impact upon the microbial population in milk and therefore has some effect on the flavor. So nobody has sent me any chats about where that bottom picture was taken based on the letters on the sign. So I shan't tell you. No, not Ireland. Actually, sorry, that's not true. It was Ireland. Mystified. No, it's not a country. Greece. That was the one I was looking for. No, it wasn't. That lettering there is Irish lettering before they adopted the Latin alphabet about 100 years ago. So that's the way that the Gaelic language was printed. So that's the same market as the picture up the top there. Right. Let's see if we can push on to the next slide. So cheese composition is rather like the foundation of structure. You need to have the right composition to get the right structure. And that's some typical values there for cheese composition. Now, I'm sure most of you will know parameters such as fat in dry matter, and if you don't, there's a formula there. It's the salt in moisture, and that's a very important measurement because it does give some indication about how the cultures are likely to grow in cheese over time, and the moisture in the non-fat substance. And you may think, why not just have salt rather than salt in moisture as a parameter? And the answer there is that that's where the salt is. It's in the moisture. Where there's protein and where there's fat, there's no salt. So in effect, what you're doing is concentrating the salt up. So for example, in cheddar cheese there, where there's about 1.5% salt on a total cheese basis, when it's in the moisture, it's something like about 4.2%. And that's what you taste. So that 4.2%, not the 1.5%. Now, I won't talk too much about that. There's a lot of detail there. If you get a copy of the slides afterwards as a PDF file, you may be able to look at that in some detail. And of course, the composition does vary quite considerably depending upon the type of cheese. And we've got baker's cheese from 0.6%. We've got cream cheese, which is not there, but that has a much higher fat content. The moisture can vary considerably from low points of something like 30 to 32%. Those would be the hardest cheese varieties you'd probably find. And the salt content also is quite considerable variation as well. And finally, the pH. And the pH is very important for dictating structure in cheese. And that varies from around about the coagulation point of caseins, the isoelectric point, which is around about 4.6, sometimes slightly below that. It's sort of like yogurt pH, all the way up to neutral. And if you wait long enough for cheeses like Camembert, you'll start to get an ammonia smell when it's overripe. And that ammonia smell raises the pH above 7 to sometimes as high as 7.5 to 8. And that's one of the few foods that we consume that's not acidic, that has a pH higher than 7. If you're interested, Icelandic shark meat is also another one, and egg yolk. Oh, and also pretzels, forgot about that one. So what are the structural elements of cheese? So we'll take a look at the largest one to start with, and that's the cheese crystals. And I will talk briefly about that because sometimes you will see an older cheese that might be in the supermarket that has a white haze on the surface. And that is most likely not mold, although it could be, but in a lot of cases, it's cheese crystals, and in particular, calcium lactate. And that can form on the surface depending upon the ripening conditions. And of course, the supermarkets throw up their arms in horror and say, well, we've got to get rid of this. And they throw it in the bargain basement bin and sell it for less, which is the time that I swoop in and buy it because it's often very indicative of tasty cheese. Very common on cheddar and Gouda and Parmigiano Reggiano. More common than other cheeses, I should say. So there's some crystals there. That one in particular one is a mineral called struvite, and they're often visible, particularly if they're more than 250 micrometers in size. The next size element is the fat globules, and I'll talk about that later in the next few slides. And they can range from 0.1 to 20 micrometers, and even larger in pizza cheese, where the fat globules coagulate. They rupture and coagulate and form large pools of fat, which has structural implications for pizza cheese. It helps it to melt more easily. It also creates a problem called oiling off when you heat pizza cheese. Now, casein micelles are the next one, and there's a picture of those, picture up the top. It's a scanning electron micrograph. It's kind of bumpy looking. That's what's called the kappa casein stabilizing layer on the outside. And down the bottom is a schematic. And if you want to get into an argument with dairy scientists, the topic to pick is the structure of the casein micelle. And there have been whole conferences devoted to this, and a lot of arguments have ensued. Perhaps war is a better word than argument in some cases. So in the middle of that calcium phosphate, holding all the protein strands together is colloidal calcium phosphate, given by these little black dots. And I'll just move the laser down here. You can see them pointing where the arrow is pointing. There's quite a few of them. Looks a bit like a plum pudding. And that gives a meaning to the purpose of the casein micelle. It creates an environment where calcium phosphate, which is needed by the calf to be able to grow bones, is packaged in a way that it could be present in a liquid product. Otherwise, it'd be present as an insoluble mineral. And so we believe that that is the evolutionary purpose of the casein micelle, is simply to package calcium phosphate in a soluble and easily available form for the calf, which of course creates cheese, which is what we eat it for. So looking at the fat content, depending on the variety of cheese, you will see different fat structures. The red, these are false colors, by the way. The red is, if I move to the mozzarella, the red is protein fibers and the blue is the fat. Now, of course, that's not their natural color. And when you stretch mozzarella under heated conditions called the pasta-filata reaction, the protein fibers align, they cause the fat globules to rupture and coalesce, and they are found within channels within the protein fibers. Cheddar cheese, a little more irregular here, but of course, if you make cheddar cheese, you'll be aware that you are pushing together or pressing curd particles at the end of the process. And that creates, you'll see here this red area here that seems to be deficient in fat, the blue fat. And that's the point where the curd particles fuse. And you'll see that under a microscope in this particular type of microscopy called confocal microscopy. Cream cheese has a lot more fat, also has a lot of these water channels, which is the black area. And processed cheese, very spherical. That's not natural cheese, of course, and that's creating basically a solid emulsion where the fat is now emulsified as fat globules, like it was originally found in milk, but different kind of structure. So look at the effect of homogenization. That's one way we can alter the structure of cheese. On the left is homogenized, and in this case, the green is the protein and the red is the fat. And we've created much smaller fat globules than you will see on the right where it's non-homogenized. So on the non-homogenized one, you'll see B is pointing at a fat globule, and they tend to rattle around in those black cages, which is where the water channels are. The green is the protein again, and if you heat and stretch it, you'll get what's seen up here at point A, which is a coalescence of fat globules, which forms those sort of like lakes of oil, which are present within the pizza cheese structure. So that's one way we can alter structure, by homogenizing milk. Over time in mozzarella cheese, first of all, on the right here, we'll see those black channels I showed you before. This is what they look like under a scanning electron micrograph. And those little indentations you'll see here on the screen are where the fat globules push into the surface of the protein. And all you'll see here is a protein, and everything else has been taken out. So it's kind of like the shell of a pizza cheese. So here it is again up the top with A, and over time, the protein swells and imbibes the water, which is found in these channels here, and it creates a more homogeneous structure. Also, if you add salt, it creates a more homogeneous structure, and much more quickly than it would within the absence of salt. So another way to alter structure is to change the salt content. So what is cheese structure? I think cheese structure is, I like to think of it the center of the universe. So everything sort of springs out of that. We'll start up the top here. The obvious thing that you will see that you'll see is the appearance of the cheese will differ if you change the structure. The texture will change. That's fairly intuitive. Also, the flavor changes. I'll talk a little bit more about that. The structure has implications for the digestibility and also the delivery of nutrients, and therefore the health of the consumer. So depending upon the structure, a lot of work is done on this in the Ag Research and the Reddit Institute here in New Zealand, and also in Canada at Laval University and other places as well, on the release of nutrients and bioactive components when you consume cheese. And we use in vitro digestive models to break down the structure of different types of cheeses and see how does it release the nutrients. And also the food microenvironment and the safety is also dependent on the structure, and therefore the shelf life. So all these things sort of spring out of structure. There's a very important quote up the top there. Cheese with poor structure makes poorly flavored cheese, but good structure does not always result in good flavor. Good to know. So we need to get the structure right to get the good quality cheese. So how is it generated through structure? And we have some structural elements here that are called macrostructure, and that is the surface bacteria on the Limburger. You'll see the blue veins within the Stilton, and you'll see the white mold on the surface of the Brie de Meaux. So these are things that are obviously visible, but are classed as structural elements. So this is how we can do it. The most obvious and easiest method is to use different types of culture to change the flavor. And that's what we've done for 100 years or more. Another way is to homogenize the milk, as I showed you before. We can alter the moisture composition. We can also try a little trick by using recombined milk and put different coatings on the fat globules. So that requires homogenization as well. And I like that idea because it's a way of exporting dry dairy products overseas, where overseas countries can add their own water and make cheese out of it. So we're not paying for the cost of the volume of shipping water overseas, or if you're air freighting it, the weight of the water. The problem with that is that recombined milk cheese tastes absolutely awful. So there are ways that, and I've worked on this for a number of years, to try and develop cheese flavors by using different fat globule coatings. Another very novel way is to alter non-starter lactic acid bacterial cell surface characteristics, so they bind to water, to the fat globules, and therefore are able to react with the fat to produce lipid-derived flavors. So I haven't seen that used in practice, but I have seen some foundational science that's investigated that. So how do you get the nice flavor of Limburger? Well, of course, an essential element is toe jam. And so you get 3 people to stomp on the milk, and that introduces the flavor. I can't hear you all laughing, unfortunately. I'm hoping you are not writing that down. So methods to alter cheese manufacture, those who make cheese will be familiar with all these techniques. And it's basically by manipulating moisture through syneresis at the manufacturing stage. So I won't go through those in detail, but they are listed there for your reading pleasure later on. Moisture control does prevent off-flavor development. That's important to know, through the growth of unwanted microorganisms, along with pH and salt. And one that I haven't added there is ripening temperature. So all of these are very, very important. So if we can control the moisture, we can control the structure to a certain degree, and therefore impact upon the control of off-flavor development. So how is flavor generated in cheese? So of course, as a fermented product. And the 3 main substrates for producing flavor are casein, the triacyl glycerides, which is basically the fat, and lactose, which is the milk sugar. And I put lactose, well, it wasn't me, it was McSweeney and Sousa who did this in this diagram, but they put lactose and citrate together as carbohydrates. And lactose is obviously very important for reducing the pH of milk to create acid, which has structural implications. And that is converted to lactic acid. If you look at Dutch style cheeses, they also have a citrate metabolism pathway, and that creates those little eyes that you see in Gouda, and also a buttery flavor that you get through a compound called diacetyl. So these are the substrates, and then all of these in a very complex avalanche of biochemical reactions produce what we know as volatile flavor compounds down the bottom. Now, why do they need to be volatile? Well, that helps us to sense it when we consume product, because when you eat food, you have to chew it and your tongue moves around, and there's air above that up into your nasal passages, which aids in the sensory perception of flavor and aroma. So note the important distinction here between flavor compounds, which are produced, and we analyze that using biochemistry. Sorry, the other way around. The volatile compounds, which we analyze by biochemistry, and the flavor compounds, which we analyze by a sensory analysis, which involves human beings. There are some, of course, important relationships between the two. So looking at caseins, a very important thing to note is if you get the wrong kind of protein breakdown in cheese, you get what are known as hydrophobic peptides. So if you use particular kinds of cultures, or if you use a particular kind of coagulant that breaks down these peptides, that can give a very bitter flavor to the cheese. So that's an important aspect to control bitterness in cheese by manipulating the kind of cultures and coagulants. So looking at these reactions here, you don't need to look at the details, but different kinds of biochemical pathways result in fruity flavors from down this pathway here. Different kinds of amino acids, which are sweet. And this is proline particularly important for the sweetness of Swiss cheese. Down here to the acids, which can have a number of different flavor profiles depending upon what kind of acid. And the one that my favorite is the sulfur compound. So you get cabbage, garlic, and cauliflower. which is absolutely anathema to American consumers. They do not like it at all, I've discovered, and they consider it a defect. But coming from Australia and now New Zealand, I do appreciate that sulfury note in some of the cheddar cheeses that are produced. And then lipids again. So looking at the red sensory terms, we get this fruity, musty mushroom, which is indicative of methyl ketones. That's a very important flavor component in blue cheese. A number of lactone-induced flavor components, the aldehydes up here, and finally the alcohols. So trying to elucidate what causes cheese flavor based on chemical analysis is an absolute haystack of a problem to investigate. And people have been coming up with long, lengthy lists of compounds to try and figure out what's important. And then more importantly, how are they produced? What kind of biochemical pathways? And again, what kind of cultures produce those biochemical pathways? So I'm going to talk a little bit about lipids. And this is a nascent fat globule. So it's being produced on the what's called the epithelial cell layer in the mammary cells. And it has a coating around it given by the arrows on that picture right here. And it's a very complicated membrane. It protects the milk globule from lipolysis and coalescence. And it contains a lot of biofunctional properties. A huge amount of research going on now in the nutritional science to understand the health implications for some of these bioactives that are found on what's known as the milk fat globule membrane. Schematic diagram right here. This is what we think it looks like. This is from a French scientist, Christelle Lopez. And you'll see the triacylglyceride. That's the interior of the fat globule here. And what protects it, that very thin layer you saw on the previous slide, is a tri-layer system. These are phospholipids, these orange with the two tails coming out of them. And the green ones here is sphingomyelin. And I'll explain why that's important in a minute. Between the sphingomyelin fatty acid chains, which are the black lines coming out of all of these phospholipids, is cholesterol. And so that's where cholesterol is believed to sit, in association with sphingomyelin. Also, you've got these Christmas tree-like things, which are embedded proteins. Some of them are transmembrane proteins. They go all the way through. Some of them, like xanthine oxidase, sit right here between this bilayer above it and the monolayer below it. Now, all of this is something like 4 to 10 nanometers thick. So quite complicated and has important implications for nutrient delivery. So the next slide, I'm going to circle the sphingomyelin and the cholesterol right here. So you might say, well, how do you know that's real? Is that really based on reality? Yes, it is. There it is right there. So this is some work I did with a PhD student of mine, Sophie Gallier. She now works for Dairy Goat Cooperative here in New Zealand, doing some really fundamental science on nutritional benefits of goat milk. This was, gosh, when was this? 11 years ago. So what I've circled there is a black circle, which is not really a hole. This is where the sphingomyelin cholesterol sits in a fat globule. So you can actually visualize where the chemical's found. That's a Jersey milk fat globule. It's around it actually is 17 micrometers in diameter. So Sophie took quite a long time to find that under the microscope. And you'll see what's attached to it, these little Mickey Mouse ears up here. That's basically the milk fat globule membrane layer without the fat in the middle. So they're sort of they're called empty vesicles. So why is this important? Well, this is where the cholesterol is. Now, cholesterol has a bit of a bad rap. If I gave you a spoon of cholesterol and then I gave you a block of cheese that had exactly the same amount of cholesterol in it, one has a very different health outcome. Giving you pure cholesterol is going to have a detrimental health outcome. Giving you a block of cheese will not. And the reason for that is that the sphingomyelin binds to the cholesterol and it stops a lot of it from getting into your circulatory system. So nature has built a wonderful product called cheese where you can eat cholesterol and not get the detrimental health effects. And there's some clinical studies to back this up that show that at worst, there's a neutral effect on cholesterol, on your blood lipids, a neutral effect at worst. But there are a lot of slightly positive effects which are significant. Good to know. So I've been promoting this for a while with the dairy industry because I think we need to talk more about the health aspects of dairy products. Of course, calcium's the obvious one that I won't be addressing here today. So that is cholesterol. So you may ask, well, why don't we just take all the cholesterol out? We actually need cholesterol. If we don't eat cholesterol and we don't get it in our system, our body will manufacture it. We need that to create bile salts to digest lipids. And by putting cholesterol there, and this is some very recent research coming out of my own lab here in New Zealand that shows that if we have cholesterol present in these kind of fat globules, the more we have, the more it slows down the digestion. So it has a very important structural and nutritional role to play. So if you don't like that picture, on the right-hand side there, we have a basketball and some tennis balls and some marbles. So that, of course, represents, I'm sure you all know, the large basketball there is the fat globule, the marbles are the whey proteins in milk, and the tennis balls are the casein myocells. And not a bad analogy, by the way, because casein myocells are furry and so are tennis balls. So there we go, a sporting analogy. So texture and flavor reactions impacted by a number of different things. It's extremely complicated to look at the different physical and chemical reactions that occur. One important one is the effect of milk fat globule extraction methods, which I'll address later on, and how we take that out of buttermilk and use that to coat fat globules to make that recombined milk cheese that I talked about earlier. Things like heating, cooling, churning, they have a profound effect on structure and probably flavor as well. Homogenization certainly does. That's used in blue cheese to amplify that lipolytic flavor. And things like pulse electric field processing, which we've done a bit of work with milk, but not with cheese. For enzymatic reactions, the enzymes that are naturally present in milk need to be close to what they react to. That's called the substrate. If they're not, there's no reaction. So that's fairly obvious that if we put the substrate and the enzymes together, we can get a desirable reaction or sometimes undesirable reaction. And of course, that is dictated by a structure. And I will talk about the matrix protection effect as well, because the enzymes don't function as they should when they're in a cheese matrix or in a fat globule matrix. I'm going to really skim through this quickly without going into too much detail. This is the composition of the milk fat globule, mostly lipids, a fair amount of protein in there, and all of these lipids have different kinds of biofunctionality on this right-hand table, which is dictated by, a lot of it's dictated by the kind of heat processes that we use to extract the buttermilk and create a powder out of it. Now, this is some very minor processing effects here, and as I mentioned before, they can have a profound effect on lipid composition and also flavor generation. So this is some work that, again, Sophie Gallier did back in 2010, looking at raw milk, recombined buttermilk, and processed milk, and she was getting very different kinds of polar lipids. Those are those orange circles with the two tails coming out that I showed you before. And that's going to create a different structure when you take those polar lipids and use it to re-emulsify milk fat to create recombined fat globules. And also, this is analogous to the proteins. You'll see there that we get different proteins coming out as well. Now up the top here, this is alpha serum and beta serum, which are byproducts of butter manufacture, and buttermilk powder and buttermilk. One of the problems with buttermilk powder is that it has a lot of very high microbial population of potential spoilage organisms. So it's given a high heat treatment to create the powder. And that unfortunately inactivates a lot of the enzymes that we want for biofunctionality. So we're looking at some non-thermal, less stringent drying processes to create buttermilk powder that retains that biofunctionality that we can use to then emulsify fat globules in recombined milk cheese. So how does fat create cheese flavor? Metabolized into the fat itself could be metabolized into flavor compounds or precursors. The fat itself could harbor flavor compounds and precursors that are fat soluble. It contains enzymes in the milk fat globule membrane layer that produce flavor. And I pointed xanthine oxidase out earlier. Provides flavor precursors from the milk fat globule itself, or just has an oil-water interface, which is necessary for lipases to function to create lipid-derived flavor compounds. So different kinds of theories, and nobody's really nailed this one down, which it is, but it's probably a combination of everything there. Lipases, of course, are enzymes. Enzymes like to be in water, but this lipase likes to react with fat. So that's why you need an interface. On the water side, you've got the enzyme. On the oil side, you've got the substrate. So that's a few theories there, and this is a micrograph using false colors again, and it shows here that the bacterial cells, which I'm pointing out using the red laser pointer, they really like to be located around the fat. And the fat is given by the red, and you'll see that they're largely non-spherical, which probably indicates that this has been, the fat globules have been ruptured and they've coalesced to create these unusual kind of structures. But these cultures like to be close to it. And there's some kind of binding mechanism that we're only just discovering between the bacterial cell surface and also the surface of this pool of fat here. And this is important for lipid-derived flavors. If the cells which contain the lipases are not close to the lipids, then you won't get a reaction. So this is quite important to try and to modify this kind of reaction, which is a manipulative technique to derive different kinds of lipid-derived flavors. So that's an important point to know. So some more foundational work was done by one of my colleagues, Rafael Jimenez Flores, which I used to work with him over in California for a while. And also John Sharp in the physics department over there in California. Oh, and Guyami from Laval University as well. I don't know this guy, number 2, a woman. So this is 1, 2, 3. So what do we have here? This is called an optical tweezer. And looking at the right, this lab group looked at binding of Lactobacillus reuteri, which is given by the yellow circles, to the surface of the red fat globules. You'll see they're sticking here. And so it was of interest to these scientists to figure out how well do they stick. So what they did is they used optical tweezers, and they took the milk fat globule and put it in what's known as an optical laser trap. And then the bacterium was attached to the cover slip of the microscope. And what they did is wait until it attached in point 2 here and drag the cover slip away. And that elongated, right where my laser pointer is here, the bacterial cell, until it finally popped off. And you can measure the force. And the binding force is not newtons, it's piconewtons. It's 10 to the minus 12 newtons. So very, very small force, but it's important for that interaction between culture cells and fat globules. And some very interesting work done about 25 years ago, which I haven't seen that used in commercial practice or any kind of practice really, is to manipulate the surface characteristics of these non-starter lactic acid bacteria so they bind more or less, depending on what flavor you want, to the fat globule surface. So let's just push on here. Some very interesting work done in 1974. I uncovered this when I was doing my PhD, not in 1974, it was 20 years later, but this was a group from, I think it was Ohio State University, that looked at a natural milk emulsion and made cheese out of it, and looked at the flavor response to see how cheddar-like it was. And the ripening period is given on the x-axis down here. For natural milk emulsions, it had pronounced between moderate to pronounced cheddar flavor, which is good. That's what you want, right? So that indicates that the natural milk fat globules are important. By the way, if you make skim milk cheese and try and eat it, as well as some very hard and rubber-like texture, you'd also get very poor flavor. So that's another reason we know that milk fat is important for cheddar cheese and in fact, all cheese varieties to varying extents. What they did is they took mineral oil, and they emulsified milk fat globule membrane material to create a recombined milk product, and they got slight cheddar flavor. It's better than no cheddar flavor. So that was rather interesting. So that seemed to indicate that the natural milk fat globule membrane was important for flavor development, not necessarily the fat that it was coating, which in this case was just an odorless mineral oil. Quite interesting fundamental research done back then. The reason it was only slight cheddar flavor was probably because when they homogenized it, they added the milk fat globule membrane layer back in a mixed up format, not in its natural format. So the enzymes are all in the wrong place and they weren't creating the flavor that you'd expect with cheese. Some work that we did 20 years ago, this was, people here might know Chakra Wijesundara. I don't know whether he's still working I think he's retired from CSIRO. Les Drury, and then these two people here were collaborators of mine from University of Wisconsin in the US. And we looked at the two things. One is the creating a recombined milk product with anhydrous milk fat, creating it with a solid milk fraction, or creating it with a liquid milk fraction. And when we had the liquid milk fraction, we saw an increase in some of these in the free fatty acids, and also in some cases some of the sulfur compounds, which is related in a sort of a poor fashion to the development of cheddar cheese flavor. So that says two things. One is that perhaps it is the milk fat that's important when it's in a liquid format. Perhaps the flavor compounds can get out more easily from the lower viscosity oil. But the other thing is that it could be something to do with the circularity of the fat globules. This is some work that I have not published, but it was looking at globule circularity. One means it's perfectly circular, like you saw in the processed cheese before. And as the fat globules get bigger, they get more deformed. And when they get more deformed, they expose more of the oil because there's not that membrane coating it anymore. So the hypothesis is that more non-circular and larger fat globules have a greater propensity for creating some kinds of lipid-derived cheese flavors. They're also more easily ruptured as well because they're larger. It's a bit like filling up a bean bag with cooking oil and sitting on it. It ruptures quite easily. But if you try to do it with a very small circle that's only a millimeter in size, it's hard to rupture it. So this is some work done 20, 25 years ago looking at, this is what cheddar looks like. This is, I think, as far as I know, the first published confocal micrographs of cheese. Back in, the work was done in 93, it was published in 95. And it's got there's been a lot of improvements since then, as you've already seen in some of the previous slides. So we can change the circularity, we can change the size. In this case, we try to normalize the size across by coating the fat globules with different proteins, alpha S2 casein and alpha lactalbumin, just to look about what does it do to the structure. And interestingly, when we coat it with this particular casein right here, it creates a very oily kind of cheese where the fat globules are easily ruptured. And we didn't taste the cheese, but it's just one way of manipulating the structure to create cheese. So these are enzymes that are found. I want to talk about two, xanthine oxidase and, oops, I've highlighted the wrong one there. That should be gamma glutamyl transferase I'll talk about, not the galactosyle. These are all found in the milk fat globule membrane on the surface. We also have enzymes found in the casein micelle and some in the serum phase as well. So I'm going to talk about those two enzymes. So xanthine oxidase is an enzyme that has oxidative properties, and it has potential for development of flavor by converting aldehydes that are derived from lipids into acids. And this is a reaction that it commonly catalyzes, the reaction of hypoxanthine to xanthine to uric acid. This enzyme is found in the milk fat globule membrane. Uric acid, unfortunately, creates these very sharp, unpleasant crystals, which is what causes gout. And so people thought back in 100 years ago that if they homogenized milk, they might release the xanthine oxidase from the membrane surface, create uric acid crystals, and therefore create gout. Fortunately, it wasn't borne out in reality. That didn't happen. And so now we have a much safer milk product by pasteurization and homogenization. and it doesn't necessarily create gout. There's no mechanism to say this is important. Right, there we go. So this is the matrix effects I alluded to before. And what I want to show you is that we get these two temperatures here. This is xanthine oxidase. If we pasteurize the milk, we get a large reduction in the activity of that enzyme at 72 degrees for 15 seconds. So 15 seconds, we're not going to pasteurize for 30 minutes. 15 seconds is way up here. So we're not getting a large amount for the 72, but with the 63, which is thermization, we typically do that at 30 minutes. So we've lost quite a bit of the activity on the blue curve here, which says that high temperature short time pasteurization has much less of an effect on the activity of xanthine oxidase compared to thermization. Interesting if you're looking at oxidized flavor profiles in cheese. The matrix effect is where it's present in buttermilk. We see a rapid drop off in activity as we heat it over 5 minutes. It's all gone by about 80 degrees. If we heat it at 65 and 75, we see less of a drop off at 65, more of a drop off at 75. But when it's present in the buttermilk, when it's naturally on the surface of the fat globule, it has a matrix protection effect. So we see less drop off than we would when it's in solution. So we looked at different techniques. This is just milk, so it's not cheese, but this is a reaction of aldehydes to acids. And if we do thermization or pasteurization, or if we even hold it at refrigeration temperature for a day, or if we add salt to it, I'm not sure why you would add salt to milk unless you're making Egyptian Domiati cheese. This is milk is the blue, and this is a recombined milk product. And we see that we can get some of that activity back of xanthine oxidase by making that recombined milk product, but we might lose a bit if we just refrigerate it. Here we gain a little bit if we add salt to it. So it's very common processing technologies, perhaps with the exception of adding salt to milk, can be used to manipulate enzymatic activity and therefore flavor production in the cheese that's made from that. So we looked at a number of ways of changing flavor profiles. One that we examined was washing. And we took a native fat globule here, and you'll see that the black circles around it, that's casein micelles. And when we wash it, we lose the casein. And then we've also washed it with what's called a simulated milk ultrafiltrate, or SMUF, which is basically the water phase of milk. And you get a different kind of profile on the surface. So that basically changes the milk fat globule membrane using these very simple washing techniques, and therefore a way of manipulating flavor development that's derived from lipids. So again, this is the emulsion. This is the raw cream. Left is the emulsion, and orange is the cream. So we've done nothing to the cream here, and we just created a recombined emulsion here. It's a little bit more activity in xanthine oxidase. Here, if we wash it, we actually gain a lot of activity because we're removing some of the surface structures that are casein-based. And we're getting more reaction, not because of the washing process here, but because we're rearranging the surface on that recombined emulsion. And the same when we're washing it with distilled ionized water as well. So the important thing here is that when we homogenize to make recombined fat globules, we are altering the natural structure and therefore altering some of the enzymatic activities. So the second enzyme I want to talk about just with this one slide is glutamyltransferase activity. And again, the same processes we used before. And this is an interesting enzyme because it produces what's known as a kokumi flavor in Gouda cheese from what are called gamma glutamyl dipeptides. And this enzyme, the glutamyltransferase, is found in the natural milk fat globule membrane in a particular position. But if we homogenize it, then we're going to change its position and therefore change the production of these kokumi flavor compounds. So this is known as one of the extra flavors. You're all familiar with the 4 tastes: salt, acid, sweet, and bitter. And here we have an additional one, kokumi, and also umami, which is sometimes not referred to as taste parameters, but more to do with flavor. So there we go. So in summary, cheese has a complex native microstructure that impacts upon appearance, texture, flavor, release of nutrients, and ultimately human health in a positive way. And we're only just beginning to explore that and getting away from that terrible dark period 20 odd years ago when fat had a bad association with health, and people were trying to get away from fat, and of course doing things worse, which was feeding people those old margarines from 50 years ago that were loaded with trans fatty acids. Fortunately, they don't do that anymore. And also making sure we eat lots of carbohydrates. So that's probably created the obesity epidemic rather than fat. That is my considered opinion. You may differ if you wish. So where are we now, and where might we head in the future? So I think going back to that recombined milk, looking at low stringency extraction methods, low temperature, to add value to buttermilk and buttermilk powders with retention of biofunctionality, and as an application to improve the flavor of recombined milk cheese. Targeted functionality of cheese ingredients. We've done that for a long time with pizza cheese by altering the manufacturing process to get different stretchability, to create less free oil, and that's old research that we understand quite well. But what about health functionality? What about nutritional functionality? How can we change manufacturing processes? Really interesting one is some work done by a colleague of mine. It was done 50 years ago in Ohio in the US, but it's been picked up more recently by some Irish researchers, looking at manipulating redox potential. That's basically the state of oxidation in the cheese matrix. And different cultures grow better or worse, depending upon that redox potential. So milk has a high redox potential in the positive range because it has a lot of oxidation because of the, when you milk it, you get oxygen being dissolved in the milk when you milk the cows. But when you create cheese, it plummets into negative values. That's a reductive environment, and important implications for the growth of non-starter lactic acid bacteria. So understanding that's important, even measuring it's important. It's quite difficult to measure it, because we had so much oxygen surrounding us that contaminates the experiment. Understanding the impact of the cheese matrix on digestibility and the release of nutrient components. We use an in vitro approach here at the Reddit Institute and Ag Research. Some of my colleagues do in vivo studies, which I think are definitely more time consuming and expensive and require all sorts of ethical approval. And then finally, the one that I alluded to before, altering the surface characteristics of these non-starter cells to control binding to milk fat globules. So I think these are really novel areas that we can investigate further to look at how we can manipulate manufacturing processes and therefore structure to impact upon flavor. In combination, of course, with the use of different cultures, which is vitally important for creating flavor in cheese, and probably the easiest way to do it, quite frankly. So when you're traveling, what 3 things do you need? Now, boys and girls, do not what I do here when I was driving. I was driving on the right-hand side of the road, which is fine. So I wound down the left window, which is fine because that's where the steering wheel is, and took a picture. You don't do that anymore. You get pulled over pretty quickly. So the 3 things you need when you travel, of course, is petrol, somewhere to sleep, and cheese. So there is a wonderful panoramic view of the city I now live in. That's downtown in the background there. And that from the bridge to the city is 2 kilometers. It doesn't look it, but it's sort of like a zoomed in photograph, I think. And I think it was taken from around the area of Massey University up on the hill. So I'm going to open up for questions. And the deal is that if you type them in the chat box, and I'm going to read the question out, and then I'm going to attempt to answer it.
Thanks so much, David. That was really excellent. I think everybody listening would realise what an authority David is on this cheese making business. In fact, I have heard that he has been nicknamed Dr. Cheese in the past.
Yeah, there's a little club. We have the Dr. Cheese Club, a few of us who did our dissertations on cheese. So.
Okay.
So questions. I have one question here from an anonymous source. not so anonymous. Can Australian cheesemakers create cheese that tastes like raw milk cheese using pasteurized milk? Absolutely. So I've changed my tune on this. Decades ago, I thought, the reason that French cheese is so great is because they don't pasteurize their milk. Not necessarily. There are ways to use cultures and ways to purchase them from culture houses to get excellent flavored cheese. And here in New Zealand, we make, not we, it's made by a Dutch family up near Auckland. It's called Maya, it's the name of their company. Now, you may think, well, and that's with pasteurized milk. So is it because they're using different cultures, or is it because they're just Dutch? I don't know the answer to that. Maybe they just have this Dutch aura about them that creates beautiful Gouda cheese. I have no idea. But we do tend in Australia and New Zealand, and even more so in the United States, to create cheeses that are safe, that are consistent, and there are no surprises to the consumer. And I refer to those as the boring cheeses. Some of them are good, but so I'm always off to the markets trying to find cheeses that are made in a different way, maybe in a more artisanal way, that are not so focused on consistency. And those are springing up all over the place. We have a lot of those in New Zealand now. Some of you might know Neil Willman, who used to work in at Gilbert Chandler College. He's over here in New Zealand now. I think he's fairly heavily involved in the Cheesemakers Association here and the National Cheese Awards that's held every year. So yes, we can. We just need to be more like winemakers and less like industrial cheesemakers.
Okay, so I've got one more question here that I was thinking of.
That was the question. I primed you with a question that I can't answer, Jenny. What are some practical ways of altering cheese flavor development that cheesemakers here today could use in their factories? Right. That's a hard one to answer. I talked about a few different processes like homogenization, and homogenization it can create problems as well as creating different kinds of cheese flavors. I think the key here is to use different experimental techniques and try to use them maybe on a softer scale than you would normally do. So maybe something like a low pressure homogenization may alter the cheese flavor characteristics, probably the lipid derived ones, I would think, more than the casein derived ones. Experiment around with different ripening conditions, different kinds of barrier bags. Maybe don't use a barrier bag, maybe use wax or some other more oxygen permeable wrapping on the cheese. Different ripening temperatures, that one's fraught with difficulty. It's a bit like predicting cheese flavor development. It's a bit like the weather. And it's known that if you ripen cheese at a let's say about 8 degrees Celsius, you can get the right rate of flavor development. If you take it to 13 degrees to try and speed it up a bit, it becomes a bit like unpredictable weather. You don't know what you're going to end up with later on. So yes, there are some different ways you can. Sorry, I'm reading a question out here. Manipulate processing technologies. This is a question I've.
Sorry, what are you reading out there? Which
I'm just I don't multitask well. I've tried great from both sides of the P word.
I just wondered, Nicole, would you like to unmute and explain that? I find your comment a little bit hard to follow there.
Oh, sorry. My point was probably better made earlier, and that is pasteurization. We can get bogged down in it as a barometer of potential for quality. And I don't think it's an argument that we should be investing too much time in, because what you've outlined in your presentation is probably more important to develop understanding of how substrates work with bacterial and enzymatic propositions to create, great tasting cheeses. The pasteurization as opposed to pasteurization thing, like I said in my comment, wasn't really a question. I've had brilliant raw milk cheeses and absolute crap. So, the more we can talk about learning about what you've just outlined in your presentation, I think the more quality and consistent quality we'll be seeing out of domestic cheesemakers. That's kind of my comment.
I do tend to agree with you on the pasteurization. I think it's sort of the realm of the artisanal cheesemakers, and some of them do not have very good practices. And when our Ministry of Primary Industries points that out over here in New Zealand, they get very upset. But I've had excellent pasteurized milk cheeses, and I've had some pretty awful raw milk cheeses. Maybe that's what you were saying before. I think you said the reverse. But it's like a cultural experience. If I was going to France, I would sample everything that I could taste there, and form my own opinions about what is good cheese and what is not good cheese. And even that's a very difficult decision to make, whether cheese is good or not. Sometimes it boils down to a personal preference, or
That's
how
totally
well it is.
Subjective.
Or
But I mean, I
well
went to Bra a couple of years ago, and I had some diabolical experiences on both sides of the fence. But I guess relating back to your content, for me, the importance as an artisan cheesemaker is understanding a lot more of what was in your presentation. And only with those fundamentals can we as domestic cheesemakers at artisan level improve. We don't have the benefit of schools aside from Castlemaine, which has been brilliant, totally brilliant, but really only come to fruition in the last 6 to 12 months to further our cause in pursuing, quality from a perspective of improving substrate and biochemical reactions with enzymes and whatnot with substrate and better practice.
Fantastic.
Yeah, I don't know what's available in Australia now. There was a cheese making school at Gilbert Chandler, but that's closed down.
It's not going now.
Yeah.
No, I think Alison and Yvonne provide a great option for us. But I guess my point is that we can get in a marketing and in a cheesemaker chat context sidetracked by talking about raw pasteurization, et cetera, as a barometer for quality, whereas we should be focusing on improving technique and milk sourcing and farming and that kind of stuff.
Absolutely.
And your content has been very insightful and helpful in that regard.
Okay, Ian Field has made a comment there. Surely some of the taste and quality is to do with the quality of milk. Absolutely, Ian.
Oh,
and
yes.
We have run many webinars on that. It's so important, the quality of the milk. Now it is time to finish up. I've just clicked on Mentimeter link there for people to give feedback. I'll also include that with the recording when that's sent through, but your feedback is really, really important. Thank you so much for today, David. It's been fantastic. And if anyone has got another follow-on idea for a webinar you'd like David to speak more about, that would be more than welcome if you send those ideas through to me. I just want, sorry, David.
If you have any questions about anything, just flick me an email. The attendees have my email address?
Yeah, well, always you can email me and I'll just put you in touch.
Right.
That's fine. And I really want to point out that I was impressed with some of the researchers who you had cited there in your presentation, being Pat Pulowski and Raphael Humane Flores. And both of them have been our webinar presenters. And if anyone would like to hear any webinars from the past, they are being uploaded more and more onto the Dairy Australia website. But these ones, current ones, won't be uploaded for another 12 months. But thank you, David. With that, I'll just stop the recording. Thank you.